So we ended the last segment putting together the equation for the control volume formulation for the conservation of energy, or the first law of thermodynamics. And we saw that we had the work term, and we need to deal with the work term. So the work term was shown right here. And I said that we needed to have a way to be able to express the different components of the work term. So that's what we're going to do now. We're going to begin by rewriting the work term as the following. So we're going to break work into a number of different components. We're going to say that work could be consisting of what we call shaft work. So that could be a shaft crossing the control boundary. We can have work due to normal stresses, and we'll call that normal. We can have work due to viscous shear, and we can have other forms of work. That could be surface tension work, it could be electromagnetic, things like that. But to define these, this was shaft work. Normal stress. And shear stress. So what we'll do, we will take these one at a time, beginning with shaft work. So it's net rate of work transferred in through the control surface. If you think to thermodynamics, quite often we'll have our control surface, control volume, and that would be something like that. Perhaps you have an impeller and you're doing work, it's rotating, and that is the process by which you are adding work to your control volume or the control surface. So the next one that we have is normal stress. So this is a work associated with a force moving through a distance. Remember, we have fluid coming into and leaving our control volume. In thermodynamics, we usually call this flow work, and we're going to go through the derivation of that. But the work itself, remember, work is force times a distance. So we have a force applied over some distance. We haven't defined what the force is yet, nor what the distance is. Now we're interested in the time rate of change of that, so we want joules per second or watts, and for that we're going to do it in the limit as delta t goes to 0 of delta W divided by delta t, putting in what we have for delta W. That's F dot ds, the distance over which the force is acting, divided by delta t. Now looking at this, that there is just the velocity that the fluid is coming into or leaving, and where our normal stresses are being applied. So we can rewrite that then as F dot v. And what about force? What we can say with force, we're going to write it generically as some normal stress, we haven't defined that yet, multiplied by some vector for the area. And so if we draw it pictorially, and if that's our control volume, we have dA here, and that will be a vector. Remember, the area always points out from our control volume. And here we will say that we have some stress, that we will have it as being the normal stress. And we'll leave it kind of generic for now. But with that for the force and with that for the work, what we can do is we can rewrite this for normal as being an integral over the control surface And what I'm going to do here, I'm going to flip the dA and the V around. It's a dot product, so it doesn't matter the order of that. And so we can go through and flip that. It'll make sense shortly why I'm doing that flip. but I'll just reverse the order of it. So we still have our normal stress multiplied by V dot dA. Okay, so that is normal work. The next thing that we need to look at is the shear stress work, or work associated due to shear stress. So this is work associated due to tangential shear stress. And just like before for normal stress, we're going to define some force, and that's going to be the differential of the shear stress vector, dA. And so if we're to look at a little element, some surface area, we would have tau being the shear stress, and I'll call that a vector. And the area that this is being applied to is dA. Now we're applying this over a distance, and so just like before, we were looking at distance, and the way that we were able to figure that out was using velocity. And so we're going to do the same sort of thing here. And that enables us to write this as work in terms of joules per second or power. So we have this. Now what we're going to do, we're going to expand this out because there can be different types of viscous shear that occurs on our control volume. Okay, so what we can have shear due to shaft work. Remember, I drew the schematic showing the control volume, and we had some shaft going through with an impeller. Right when you cross there, you can have viscous shear on the shaft itself, but that's usually already accounted for in the shaft work. So already in W dot shaft, so we don't have to worry about that one. The next one is shear on a solid surface, and that would be shear if our control volume is along a solid surface. Now the thing about that, at a solid surface, if you recall the no-slip boundary condition, we have V is equal to 0, and consequently that term goes away. And then finally we have the one for crossing at ports. And if you create your control volume in a manner that the control volume is normal to the flow crossing that boundary, then we would have tau is perpendicular to V, and if tau dot V and they're perpendicular, that will equal 0. But we don't always necessarily have that condition, and so we will retain this last term. But the other two will go away through careful choice of the control volume, as well as the fact that the shaft work is already in the shaft work term. So what we end up with for shear is the following. And I write this as area of ports. That's wherever mass is crossing our control boundary, so inlet or exits. So with that, what we can do, we can expand out and write the work term as follows. We have the shaft work plus the normal stress work plus the shear term, which we isolated that only to be at the ports, and then work other. So with that, we can take this now and put it back into our control volume formulation for the first law, and what we end up with is this. And one thing that I'm going to do here, I'm going to take the normal stress term, this one right here, And instead of putting it on the left-hand side of the equation, I'm going to move it over to the right-hand side of the equation. It'll make sense in a second why we're doing that. And so here is our normal stress term. And you'll notice V dot dA that we have in the normal stress term is consistent with what we have there. And that was the reason why we did that flip around with the dot product. Now that we have this, what we can do is we can do some combinations. But what is the normal stress term? If we think about it, sigma NN, that is, I drew it originally as being the area. So that was our area, I think I said dA, and then we had sigma NN. In a fluid, any of the fluid systems that we're going to look at, the normal stress is really pressure, and it does not act outward like I've shown. It actually acts in that direction. Therefore, sigma NN is actually equal to minus P. And so we can make this substitution here up into this equation and rewrite the formulation for our control volume. And what we end up with is this. Our shaft work, shear on the ports, other. That could be other forms of work, surface tension, electromagnetic, things like that. Usually things that we don't consider, but they could be there. And you'll notice what I've done here is I've pulled in the P term, and I put P over rho because we have rho here, and P over rho times rho is then just P, which is what we had originally with the normal stress. Now, there is a thing that I can say about that. P over rho, 1 over rho, if you recall, that is just our specific volume that we look at quite often in thermodynamics. So really that term there, the P over rho, is actually equal to P times the specific volume. And if you remember from thermodynamics, we had internal energy plus PV is equal to enthalpy. So that is essentially the enthalpy term, and that's the term that's associated with the flow work that you would see in a thermodynamics course, which is consistent, and it should be, because the conservation of energy in fluid mechanics should not be different from the conservation of energy in thermodynamics. And so what this is conservation of energy . And it is in the control volume formulation. So it enables us to apply it to situations where we have fluid crossing the control boundary. So what we're going to do in the next segment, we're going to do an example problem of applying the control volume formulation for the conservation of energy to a system, and we're going to look and see how to apply it.